Okay, hi everyone. It's 1 o'clock now, so let's go ahead and get started with today's lecture for machine learning. This is lecture 3, so today we're going to be focusing on linear regression. So this will be the first model in this course that we're going to be exploring. I'm sure many of you have seen linear regression before, at least heard of it, but we'll be approaching it from sort of an optimization perspective, and we'll be learning some tools that we'll use throughout the rest of the quarter in the context of this regression problem. So before we get started with the content of today's lecture, just a couple of announcements and reminders. The first is that homework 1 is due in 1 week from today. So as always, I really recommend you guys start working on that early if you haven't already. So after today's lecture, you should be able to finish the first 2 problems. And for a little bit of context, the first problem is about NumPy and data visualization, so that's from Wednesday's lecture. And then problem 2, which you'll be able to solve after today, is all about linear regression and gradient descent. And in fact, you'll be implementing this gradient descent algorithm that we'll cover today as part of your homework. So make sure you pay attention today. It'll be important for your homework. So in today's lecture, we will introduce linear regression, introduce some notation, give you guys some intuition for what this model is. Then after that, we'll see some methods on how you can actually learn linear models using this algorithm called gradient descent. Okay, so let's just jump right into it and start discussing linear regression. So a few reminders on notation. Here we're working with a regression problem, so it's a supervised learning setting where we have some feature vectors x, again these are these bold-faced x variables, with d potential features in each of our feature vectors. We have some corresponding target variable y, which is some real valued number, because this is a regression problem. And in our training data, i.e. the data we went out and collected and that we're going to use to fit our model, this consists of pairs of essentially data points xi and their corresponding targets yi. So in Wednesday's lecture, we saw some examples of what regression problems look like, but just a quick reminder of what you can do with regression. If you're interested in, say, finance, you might be interested in predicting the stock market of a particular stock tomorrow, maybe the value of Apple or whatever stock you own. And your features here could be something like stock market performance from yesterday, various economic data, data coming from the past week, the past month, the past year. If you're interested in like a health setting, you might be interested in predicting maybe the time until the reoccurrence of a cancer diagnosis. Here, your features could be some kind of medical data about your patients, so things like test results, physiological information like body weight, height, age, this kinds of stuff, so on and so forth. So just keep in mind that regression is a very general problem, and whenever we're trying to predict just some real number based on some inputs, that's the kind of task we're trying to achieve here with regression. And some more reminders on notation from Wednesday's lecture. If we have more than one data point, we'll often take all our data and stick it into a big matrix. We'll use caps and a bold font to represent any matrices in this course. And so a bold-faced capital X represents a data matrix, where every row in this matrix corresponds to an individual data point, so an individual feature vector. We have n of these rows, so n data points, and we have d columns, 1 column for every different feature. Since this is a regression problem, we also have some vector of real valued targets y. So y1 is the target for the first data point, and so on and so forth. Okay, let's look at an example of a regression problem in 1 dimension. So here, we just have a single input variable, i.e. we're just looking at a single feature. And from this feature, we'd like to predict some real valued number y. Here we went out and collected, say, maybe 25 data points, and we're just plotting them in a scatter plot. And what we'd really like to do is not just make predictions for the data points that we went out and collected, but we'd like to make predictions for the value of y for new data that we didn't see during training. So we have some new value of x sub new, and we'd like to make some kind of prediction of what the y value should be for this x input. And of course, if you stare at these data points, you'll notice there's a pretty clear linear trend in this data. So as x increases, y also increases, and it's clearly linear. So what you could imagine doing in a linear regression problem is somehow finding the line of best fit. So we'd like to draw a line through our data that somehow explains the data in the best possible way. Okay, let's put some notation to this. The equation of a line, as I'm sure you're all familiar with, we can write as f of x given theta. So that's over here on the left-hand side. So f is our sort of prediction function, or our prediction model, that takes in a data point x and is conditioned on some parameters of this model. And what I mean by parameters here is theta naught, which is just some number corresponding to the intercept of our linear model, and some other number, theta 1, corresponding to the slope of this linear model. For a little piece of machine learning jargon, oftentimes people in the ML field will call this intercept term a bias term. So if you hear that word bias, just think it's an intercept in some kind of model. Here in this linear model, we have what are called parameters. These are essentially the weights of our linear equation. And here, in a 1D linear regression problem, the parameters of our model are just this collection of the bias and the weight corresponding to x1. So we have a total of 2 parameters in this model, theta naught and theta 1. I'd like to point out here that this parameter vector, theta, is actually unknown. We don't know what values of theta naught and theta 1 are going to give us the line of best fit. But what we're going to do is we're going to go out and leverage our training data to somehow figure out what the value of theta naught and theta 1 should be. And what we can do after learning theta, so we figure out the best slope and the best bias for this model, you can then use that value of theta to make predictions for new inputs. So all we got to do is take our x new, our data point we didn't see during training, stick it in to our linear model, and we'll get out some prediction for the value of y, which will denote maybe y hat. So again, classic linear regression. I'm sure most of you guys have seen this. So the example I showed so far is for linear regression in 1 dimension, so you only have 1 input variable. Here's another example of linear regression where you could have 2 different input variables. So here, maybe, your first feature corresponds to someone's seniority, how long they've been working for some particular company. Your other input variable, x2, might be how many years of education they have. And then based on that, you might want to predict, say, the income of this person. We're no longer trying to find the line of best fit because we're now in a higher dimensional problem, but instead we're trying to find sort of the plane of best fit. So if you sort of plot all of our data points, you can kind of see there's a plane that matches our data pretty well. In this case, we need to change the equation for our prediction model a little bit. Rather than just being theta naught plus theta 1 x1, we also have a new parameter, theta 2, corresponding to the weight for that second feature, x sub 2. Or in other words, the parameters of our model are now that's a 3-dimensional parameter vector, where the weights are theta naught, theta 1, and theta 2. So here's another example, just showing again the same thing I showed you before. On the left-hand side, we have 2 input variables, x1 and x2. Just based on visualizing this, we can see there's a pretty clear linear relationship in this data set. And then after fitting our linear model, we get out some kind of plane, some hypersurface that's fitting our data. And just like in 1 dimensions, we can then use this plane to make predictions for new data points that we didn't see during training. Of course, we can do linear regression in higher dimensions than just 2. So you might have 100 different inputs to your model. Gets a little hard to visualize beyond 2 dimensions, though, but this is really the geometric intuition you should keep in mind for any linear problem. The idea, again, we have some plane, some linear surface we're trying to match to our data points. Okay, let's introduce some notation now, just to set the stage for how you do linear regression in sort of arbitrary dimensions. So let's say now I have a feature vector, x, with a total of d different features. So we have d sort of variables for every data point. What you should notice is that I actually added a 1 to this feature vector, so I just appended a 1 at the front. And I'm kind of creating like a fake feature here, which I'll call x naught. And I'm just going to set x naught to be equal to 1, a constant. And this is mostly for notation purposes. It'll help us account for the bias term in the next equation that we'll see. Our equation for our linear regression model then, so again, f is our sort of prediction model taking in inputs x, is then theta naught, our bias term, plus just theta 1 times x1, so the weight for the first input, and so on and so forth, all the way up to theta d xd for our final input. A really convenient way of writing this, so we don't have to write out every term here, is just as a summation. So we'll sum from k equals 0 up to d, so a total of d plus 1 terms in this summation of just theta k times xk. And if you guys are familiar with dot products, you can also write this as just a dot product between your parameter vector theta and your input feature vector x. And here, I'd like to point out that theta naught doesn't have an x naught term next to it. But since we defined x naught to be 1, just a constant, we could also write this as theta naught x naught, and it just lets us write it in this really convenient form as just a summation. Okay, so any questions on linear regression? So theta 0 is some number corresponding to the bias. Theta 1 is like a weight corresponding to the first feature x1. But we could also write theta 0 is theta 0 x0 if we just set x0 to be 1, right? So we made like a fake feature. Yeah, that's right. Each of these weights are kind of independent weights. Yeah. Okay, other questions on the linear regression model that we've set up? Cool, no questions, which hopefully means things are clear and not so confusing that you don't know what to ask. Yeah, go ahead. Yeah, absolutely. Yeah, so there's no real good way of visualizing this even in 3 dimensions. So if you have 3 input variables, you need some 4th dimension for the plane. So you can't really visualize this beyond 2 dimensions, but you should have the same intuition. It's some flat surface. There's no curvature to it. It's basically a plane in higher dimensions. Yeah, so this is just a dot product. So theta is a parameter vector corresponding to theta 0, theta 1, theta 2, all the way up to theta d. X is this feature vector corresponding to 1, x1, all the way up to xd. And if you just write out the formula for the dot product between 2 vectors, yeah, it's theta 0, x0 plus theta 1, x1, so on and so forth. So it's just a shorter way of writing the same thing we wrote before. Okay, cool. So I've shown you guys the equation for linear regression models, but I haven't told you how you actually find those parameter values that will lead to the line of best fit. So in 1 dimension, you could just probably write down the equation for this line. You could stare at this for long enough and guess what theta 0 and theta 1 should be. But there's possibly many different lines that seem like reasonable guesses for what could be the line of best fit here. So the green line, the orange line, and the black line, all from, at least at first glance, look like pretty decent fits to this data. So maybe let me ask you guys, do you have any ideas on how we might measure how good a line is? How good of a fit it is to the data? Yeah. Yeah, exactly. That's a really good idea. So to reiterate, the suggestion was we can look at the data and measure how far away the data points are from that line. And then essentially using those errors, that can give us a sense of how good a line is fitting the data. Cool. So that's exactly the key idea here in linear regression. We'd like to find the model that somehow minimizes the prediction error on our data. So in this plot here, I have a bunch of data points. These are the red dots. It's a 1D regression problem. I have some blue line that I fit to this data. This is, again, just the equation for linear regression. And the vertical black bars are sort of the errors or the distance between my prediction coming from my model, the blue line, and the actual data points, which are the red dots. And what we would really like to do is find the line that somehow minimizes the total number of errors that we're making, i.e. it's going to minimize, sort of our predictions. Okay, let's formalize this a little bit, give it some notation, put it into math. So anytime we have some function that takes in parameters, i.e. takes in some kind of model, and spits out a number telling us how good that model is, we're going to call it a loss function. So on the left-hand side, we have a loss function, L of theta. Again, it takes in our parameters and tells us how good the parameters are. And for linear regression, we're going to use the following loss function called mean squared error, or MSE. And what this MSE function is it's an average over all the training data points. So we have n data points, and we're just summing over them and dividing by the total number of data points. What we're going to do then is we're going to look at the true target for the ith data point. So y sub I is the actual value we're trying to predict. Then we take the ith input, so the ith feature vector, we stick it into our linear regression model, f of x, and we get out some kind of prediction for that data point. Then we compare them. We just look at the difference between the true y value and the predicted y value coming from our model, and then we're going to square them. And the reason we square these errors is because we always want our errors to be positive. It doesn't really make sense for us to consider negative errors here. And so we look at the error for every data point, square it, take the average, and then we get this so-called mean squared error loss function. And again, the idea here is we'd really like to find the values of theta, the weights in our model, that are going to minimize this mean squared error loss. So to help us illustrate what's going on, this blue line has the lowest MSE value of all the possible lines we could draw for this data set. This black line is, visually clearly a worse fit for our data, but we can really sort of quantify this or, formalize it a little bit by looking at its MSE. And in fact, that black line has a higher MSE than the blue line. And another example of a worse fit, this again has a higher MSE than the blue line. Okay, so as I mentioned before, this loss function is really a function of the parameters. So L is some function that's going to take in our model, defined by the parameters theta, and spit out a number telling us how good that model is. We can actually visualize this loss function in a very nice way. So let's say we're doing a 1D linear regression problem. So our weights then are theta naught and theta 1. We have two parameters. And if we take those parameters, plug them into our loss function, i.e. measure the MSE, we'll get out some value for the loss, corresponding to how good that line is, corresponding to those parameter values in theta. And what you'll get out is some kind of loss surface. It's essentially a way of visualizing our loss function. It's a little hard to see what's going on, so we can also include some colors here, where red values are going to correspond to a higher value of the loss, and blue colors are going to correspond to a lower value of the loss. Another way of visualizing this is we could draw sort of contours on our loss surface. So every point along the red line here has the same value of the loss function. So all of these parameter vectors theta are kind of equivalent in terms of MSE. Visualizing things in 3D is pretty hard, so we can kind of squash things down into 2 dimensions and get another visualization here. It's the same loss surface, except instead of showing you the height of this loss surface, just showing you the colors. So again, blue is low loss values and red is high loss values. And we can also do this in terms of the contours, so we just showed sort of the contours of this surface as well. And so my point here is you can really think of this loss function in a kind of geometric way. It gives you kind of a surface that's representing how you can map between parameter vectors, theta, and how good they are by measuring their loss. Okay, so any questions? Yeah, in the back. Yeah, absolutely. So to reiterate the question, it was essentially, do higher values of theta for certain parameters correspond to more relevance? And yeah, you're exactly right. So if you had a theta value of 0 for a particular feature, it wouldn't influence the prediction at all. It would kill that feature, basically. And we'll see an example at the end of today's lecture that basically demonstrates that. Yeah. Yeah. So in the MSE, I said that we square it to make things positive. But another option here would be to take the absolute value of these errors. And the reason we do that is that squaring it is actually a differentiable function, whereas if we take the absolute value, it's not differentiable. And for gradient descent, which is the algorithm that we're going to use to actually find the value of theta, you need to be using a differentiable function. And so it's mostly for computational reasons. You could do absolute value, but you run into some practical issues. So by differentiable, I mean we can actually compute the derivative of this function. If you look at the absolute value, it's v-shaped. You can't differentiate it at the kind of base of the v. Leads to all kinds of practical problems, yeah. Yeah, another question. Yeah, so the question is, shouldn't the loss function be just a number? And you're right, but it's a number for every particular choice of theta. So if you give me a parameter vector, so you give me a value of theta naught and theta 1, I can plug it into the loss function and get a number. What I'm plotting here is I vary the values of theta naught and theta 1 and look at all the outputs of this function. This is more for intuition purposes, but we'll see how this kind of geometric picture of the loss function leads to the gradient descent algorithm in a minute. Yeah. Okay, other questions? Yeah. Yeah. Yeah, blue is good here. Okay. Now let's move on to the second half of today's lecture, which is how you can actually learn linear models using this gradient descent algorithm that I've been alluding to so far. So again, we want to somehow find the parameter vector theta that's going to minimize this loss function. So we have an optimization problem here. And I'd like to give you guys some sort of physical intuition for a heuristic way we might be able to do this optimization problem. So imagine for a second you only have a single value for theta, i.e. theta is one-dimensional. And imagine your loss surface that I was plotting a few slides ago is sort of this parabola shape. Now imagine you somehow initialize the value of theta, maybe randomly. We just pick some value for theta. And if we plot it maybe as a ball, it's like some ball we put on our loss surface at this initial random point. And thinking of things in kind of physical terms, if we're trying to minimize this loss function, we just want our ball to roll downhill until it hits the bottom of this parabola. And really this is what gradient descent is doing. It's taking some initial random value for theta and just moving it downhill until it minimizes the function we're trying to optimize. In order to actually do so, we're going to compute what's called the gradient of this function. If you guys haven't seen gradients before, just think slopes, derivatives. And what we're trying to do is move this ball downhill by following the gradient, following the slope, until we find a minimum of this loss function, which is where the gradient is 0. Yeah. So I'll show you an example of calculating the gradient for MSE, but yeah, don't worry about having to calculate gradients and stuff like that. So they're essentially equivalent. So the point where the slope is 0 corresponds to the minimizer. But the problem is we can't often do the algebra or do the math to explicitly solve for that value of theta. So gradient descent it's a local algorithm. You start with some guess and just make it better and better and better. And so you don't actually need to do that sort of hard algebra to solve for it. Okay, so maybe in the interest of time, I'll hold off on some questions for a minute. So, of course, that picture I showed you is only for one dimension, but it's good intuition for what's really going on in gradient descent. But of course, in even a simple problem like linear regression, we have a whole lot more than one parameter value we're trying to optimize. But again, this idea of rolling a ball downhill still applies. And what we're going to do is use this thing called the gradient. And this gradient is really sort of a vector that points downhill on our loss surface in the direction of steepest descent. And again, if you guys aren't familiar with gradients, just think of it as like a multi-dimensional version of a slope or a derivative. Okay. So if we have some function of multiple variables, the gradient is a new vector corresponding to all of the partial derivatives of this function. So in our context, we have some loss function, L of theta, which takes in a whole bunch of different parameter values. So it takes in theta naught, theta 1, all the way up through theta d. The gradient of our loss function is a vector-valued function. So it takes in a parameter vector theta, and it spits out a new vector, where the components of this vector are the derivatives of our loss function with respect to each of our different parameters. So we'll differentiate our loss function L with respect to theta naught and get the first component. We'll differentiate L with respect to theta 1 and get the second component, so on and so forth. And if you haven't seen partial derivatives, they work just like ordinary derivatives, except we basically fix all of the variables that we aren't differentiating with respect to and treat them like constants. So if we want to differentiate something like xy, so just the function x times y, with respect to x, its derivative is going to be y, and vice versa. So if we want to differentiate xy with respect to y, its derivative is x. If you guys aren't comfortable with partial derivatives, they're really not too bad if you know kind of Calc 1. And I'd really recommend maybe checking out some online resources and maybe trying out a few simple problems with these. So as I've kind of alluded to throughout this lecture so far, the gradient is a vector. And a very cool property about this vector is that it actually points in the direction of sort of steepest ascent on our loss surface. So it tells us what direction we can move in to increase our loss function by the kind of most possible amount. As a consequence of that, the negative of the gradient, i.e. the vector that is just flipped from the gradient, points in the steepest downhill direction. And the idea of gradient descent, then, is we can find this direction of steepest descent and take a step in that direction and use that to somehow update our parameter vector over time in order to move towards a minimizer of our loss function. And again, at a local minimum of our loss function, the gradient is going to be 0. And then we won't be making any more updates because there's nowhere we can move that's going to decrease our function anymore. This leads to our update equation for the gradient descent algorithm. We'll see this algorithm, probably 25 times during the course of this course. It's, quite general. But today we'll see it just in the context of linear regression. But again, the idea is that if we want to update our parameter vector to some theta new, we can start at some value for theta, theta old, and take a step in the direction of the gradient, where the size of this step is controlled by a parameter lambda, which is called the learning rate or the step size. So again, we start with some value of theta and move downhill in the direction of the gradient, where this lambda controls how far we move in that direction. There's some nice theory that tells us if we actually choose our step sizes wisely, we're guaranteed to converge with this algorithm to at least a local minimum of our loss function. Okay, so to kind of put things into maybe like a pseudocode perspective, the way gradient descent works is that in step 1, we just randomly initialize our parameter vectors. So in linear regression, in maybe 1D, we'll pick a random bias and a random slope to start out with. It's not going to be a very good, line. It's going to be some random line. It won't match our data at all. We compute the gradient of our loss function at that point theta. That gives us the direction of steepest descent. We can do a convergence check then. If we're already at a local minimum, there's no point in updating theta. If it hasn't converged, then we'll just plug it into that gradient step, a gradient descent update algorithm I showed on the previous slide to update our parameter values. Okay, and then shown in gray here, this is really kind of the basic iteration loop of gradient descent. We keep updating our parameter vectors using that algorithm. So I'd like to give you guys a nice visualization of what gradient descent might look like for a really complicated loss surface. So here I just have two parameter values, theta naught and theta 1. This might be some regression problem with just one input. And this surface represents the value of L of theta, like I had shown you guys a few slides ago. In gradient descent, we might start our parameter vectors randomly, corresponding to this point here. We kind of roll this ball downhill, following the direction of steepest descent, till we end up in some minimizer, maybe over here. Okay, I can take maybe one or two questions. Yeah. Yeah, so the question is, how do you actually pick the step size or the learning rate? And in practice, it requires a lot of experimentation. So it's one of those things where you try a value, see how it works, try another value, so on and so forth. Typical values for the step size are usually pretty small, so in the order of like 10 to the minus 2, 10 to the minus 3, quite small numbers here. Yeah, you have a question. Yeah, so the question is, how do we know that we're looking at a local minimum and not a maximum when the gradient is 0? And you're right, you would have to look at like the second derivative to determine that. But in practice, if you have imagine you have some peak, right? If you're not directly at the top of the peak to start, you're like a little bit to the side, you won't move uphill with gradient descent. You're gonna move downhill. So it kind of pushes you away from maxima. Yeah, you're right. So gradient descent does not always converge to the global minimizer. It's not the best model. It might get stuck in a local minimum, which is some suboptimal model, actually. We'll see more about that on Monday's lecture, actually. So thank you. Good questions. Okay, maybe in the interest of time, I'm going to move forward. So from here, we have an idea of how gradient descent works. And the only thing missing that we need to actually implement this algorithm and fit a linear model is the gradient for our MSE loss function. And so now I'm going to go through kind of difficult calculation to actually get that MSE gradient. Don't worry about trying to reproduce it. I won't ask you an exam question where you have to calculate the gradient of the MSE. But it's good to have at least seen it once and see the steps that are involved in doing this. And in practice, we'll get an equation here that you can kind of just implement in code once you understand at least the notation. So again, I have some input variable x, where I've included this kind of bias term, x naught equals 1. I have my equation for a linear model, f of x given theta, and I wrote it in this summation form, so this is just a linear model. And I'm going to introduce some new notation here, which I'll call the error. And in this error, what I'm going to do is define e sub I as y sub I, so the true target for the ith input, minus my prediction for that input. In other words, this is y sub I, so the true target, minus, I just plug in my expression for the model, minus this sum over thetas times x's. Doing so, I can rewrite my mean squared error loss function as L of theta is 1 over n times the sum of these squared errors. So I haven't really done anything here except introduce some new notation that makes our lives a little bit easier. Okay, so again, this is our MSE loss function. And what we need to compute from this loss function in order to run gradient descent is this gradient vector. This gradient vector, again, is this vector corresponding of all the partial derivatives. So the derivative of L with respect to theta naught, so on and so forth. So to actually write down an expression for this gradient vector, all we need to do is be able to differentiate L of theta with respect to any one of our particular theta values, let's say theta k. And this will apply for any value of k between 0 and d. So we're kind of computing all of these just in one go. Okay, lots of equations here, but we'll step through them. Don't get too nervous. So again, we're trying to just basically differentiate this loss function L with respect to the value theta k here. So in this first step, all I do is I replace L of theta with that expression I showed you a few slides ago. So just substituting in the value. I can pull the derivative through the sum. So I'm just taking this derivative and putting him right here. In my next step, I'm going to apply the chain rule to actually differentiate this variable e sub I. So if you apply the chain rule, we see that this expression is the same as differentiating ei squared with respect to ei. This is basically just like differentiating x squared. And then here, we'll need to differentiate e sub I itself with respect to that parameter value theta k. So if I differentiate ei squared with respect to ei, again, it's basically just an ordinary derivative. We'll get 2ei, so nothing fancy happening. And here, I just rewrote this error e sub I as that expression we had on the previous slide. So it's the difference between the true target, again, and the predicted target coming from our linear model. Okay, continuing from the last slide where we left off. The first line is the exact same thing that we previously had. In this next line here, what happens is that we're differentiating this big sum with respect to theta k. Okay, and what happens is that yi doesn't depend on theta k. So it's like differentiating y with respect to z, for example. It doesn't depend on theta k, and so its derivative is going to be 0. So this term drops out. It's a 0. Here, the only term in this summation over j that depends on theta k is the actual kth term in this summation. So it's theta k x sub ik. And if we differentiate theta k x sub ik with respect to theta k, you'll be left with just a negative x sub ik. So again, it's pretty similar to just calculating ordinary derivatives, except we've got extra variables floating around. I could pull the negative sign out to the front and the 2, nothing fancy happening here. And again, I can rewrite my e sub i's in that formula that I had previously. And we're done. Not too bad, maybe 10 lines of calculus, but hopefully not too scary. And again, the idea here is we're using this to compute the gradient vector. So we have a formula for each of these terms here in the gradient, and all the stuff here is relatively straightforward to compute. It's just a bunch of additions and multiplications. So we can plug everything into this gradient and get a fairly simple expression for gradient descent for linear models. Okay, so let's go ahead and put everything together. Theta new is again our updated parameter vector. Theta old is where we currently start at the current iteration of gradient descent. We're trying to take a step in the direction of the gradient. If we plug in that calculation we did in the previous couple of slides, so all I'm doing is plugging in this expression for the gradient. And what we see is that for each parameter, i.e. theta sub k, corresponding to the kth input in our model, this is the equation for gradient descent. Ignore this plus sign, it's a bit of a typo. It should be just lambda times this expression. And so, as I said, this is fairly simple to compute. We just need to look at our current parameter value, multiply lambda times 2 over n of this sum. We need to compute the error for every data point, and then just multiply it with the current x value for that data point. Then we can do this for every value of k. And in fact, in NumPy, as you guys saw in problem 1 of the homework, you can do this in a vectorized fashion. I.e. you can do all of these updates for each of the k different parameter vectors in kind of one line, just via vectorized operations. And one thing I'd like to point out now is that the MSE loss with a linear model is actually what's called the convex loss function. So if you plot that loss surface that I was talking about before, it'll be kind of bowl-shaped. And as a result, it actually has only one unique global minimum. This means we don't run into that problem that got briefly mentioned of kind of hitting local minima or having to worry about maximums or anything like that. And so in some sense, fitting linear models with gradient descent is actually, a fairly straightforward optimization problem. Once we do the hard math part. Okay, let's look at another visualization of what gradient descent actually looks like. So on the left-hand side, I'm plotting things in kind of parameter space. So this is for a 1D linear regression problem. So we have two weights, essentially. On the horizontal axis here, this is sort of my bias term, theta naught. On the vertical axis here is my weight term corresponding to the feature. And when I initialize gradient descent, I just pick random values for the slope and for the bias of my model. And that's this black dot here. And again, the intuition for gradient descent that you should have is you take this black sort of dot, you roll it downhill in this lost surface. On the right-hand side, I'm plotting things in what I'll call sort of the data space. So here, these red dots are my training data points. So the x-axis here actually corresponds to the feature, and the y-axis here actually corresponds to the y values. So my red dots are my training points. The blue lines correspond to the prediction errors, so how far away my prediction is from those red dots. And the black line corresponds to the current model, i.e. this is the equation of the line corresponding to this black dot for these parameter values. So as I had mentioned before, if we just randomly initialize theta, this obviously is not a very good fit to our data. Let's now take one step of gradient descent. And what you see happens is this black dot now kind of moves downhill and towards the minimum of this loss surface. And that minimum is down here, kind of sitting at the bottom of this bowl-shaped function. And on the right-hand side, plotting things in the data space again, we see our line of best fit has definitely improved. It's a whole lot better than this one, right? Still not perfect though, so let's do 10 more steps of gradient descent. So we've now done 10 iterations. Again, our parameter values, theta, move downhill towards that minimizer, and our line of best fit gets even better. Okay, 30 iterations, same deal, even better. 90 iterations, okay, now we're pretty close to the minimizer. Even though we might not, actually reach that specific point that minimizes things, we'll get basically arbitrarily close to it. Okay, so that's gradient descent for linear regression. Any questions? Yeah. Yeah, so let me go back a few slides. The question is essentially, how do you decide when to stop doing gradient descent? And there's a couple of different ways you can choose to do this. So one thing that you can use to detect convergence is if the gradient is 0. It's never going to be exactly 0, of course, so you can set some small threshold. And if the size of your gradient, usually the norm of the gradient, because it's a vector, essentially how long that vector is, if it's smaller than that threshold, then you can stop. So if it's smaller than 10 to the minus 4 or something very small like that. That's probably the go-to for this kind of problem, yeah. Cool, other questions on linear regression, yeah? Yeah, so we can see here that it's approaching the minimum, but doesn't kind of shoot past it. And if your learning rate is too big, you'll take a step over the minimum, actually. And so you kind of bounce around the minimizer and not actually kind of land in the bottom of this bowl-shaped function. We'll talk more about that on Monday's lecture, but yeah, you're exactly right. It's good intuition. Yeah, you have a question? Yeah, cool. So to reiterate the question, it was, maybe let me demonstrate the question with an example. If you only have something like 10 data points, you maybe can draw a line going exactly through those 10 data points. But if you go out and collect more data, they might not lie on that line. And so you can run into this problem called overfitting, where you essentially fit the training data too well, and it doesn't generalize to new data that you might want to go out and test your model on. We'll talk a lot about that on Monday's lecture, but yeah, thanks. Yeah, in the back. 35, yes. So this plus sign here, delete it, it's a typo. It should be lambda times 2 over n times the summation, yeah. Yeah, I'll update these slides and post a new version on Canvas with the typo fix. Okay, other questions? It should be plus, so we have a minus lambda times the gradient. And if we go back here, we actually have a minus sign for the gradient. If you guys want a fun homework problem, if you're bored on the weekend, you can think about sort of the intuition for what this gradient step update is saying. So like, why does it have this form? And if you think about it, it has some nice geometry going on. So if you're really bored at a party on Saturday night, you can bust out your Notes app and draw some pictures for this. Okay, maybe in the interest of time, I'm going to move on with the rest of the slides, then I can take some questions outside afterwards. So I described to you guys this gradient descent algorithm that we can use to actually fit linear models. Here I'm going to tell you about an alternate to gradient descent that you might have heard of if you've taken like a statistics course before. One thing I'll point out here is I'll include a little danger icon on slides if it's stuff you guys don't really need to worry about the details of. It's kind of advanced topics that are just there for your enrichment. But if you guys are familiar with linear algebra at all, you could actually write down the solution for this optimization problem directly. So as someone had asked earlier, yeah, you can actually find where the gradient is 0 and sort of do it analytically, rather than doing it with this numerical method. This doesn't work for all problems, but for gradient descent on linear regression, it's simple enough that we can actually do this. So we can write down a formula for the line of best fit, which is theta is this expression here. Don't worry about the details of it. You might be wondering, like, why don't we just use this instead of gradient descent? And the reason is that in most machine learning applications, the number of features you have in your data set is very large. And trying to do a numerical inverse of a very large matrix here, just numerically very challenging. You can run into all kinds of things like numerical instabilities, things can blow up to plus or minus infinity. Just practically very challenging to do this on large data sets with lots of different features. Another aspect of why you would want to use gradient descent over something like this, analytical expression here is time complexity. So if you have a huge data set with a ton of features, so D is very high, we see that this analytical solution, if you think about this a little bit, scales like O of D cubed. So it's cubic in the number of features you have, which, for a machine learning problem at like the scale of something like Google or Facebook might be doing, D might be on the order of like 1 million. So, cubic in 1 million dimensions just ain't gonna cut it. In contrast, the gradient descent method is actually linear in both the number of features D and the total number of data points. So for very large scale problems, this gradient-based methods can actually get you, quite a bit of speed up if you're trying to fit these models. Okay, let's look at a real concrete example just to wrap up on this so-called diabetes data set. It's a pretty popular small data set in machine learning. It's available in scikit-learn, which you guys will get comfortable with, where we have 442 data points, 10 input features, and we're doing a regression problem. And if we find the line of best